We now discuss the solution of a problem from the section complex analysis, and the problem is on the singularities of a given function. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022, and it is from the part C. The given question is, consider the function f of z is equal to sin z to the power of m by 1 minus cos z to the power of n for 0 less than mod z less than 1, where m and n are positive integers. Then z is equal to 0 is, we are given four options. Option 1, a removable singularity if m greater than or equal to 2n. Option 2, a pole if m less than 2n. Option 3, a pole if m greater than or equal to 2n. Option 4, an essential singularity for some values of m and n. We are given a function f of z is equal to sin z to the power of m by 1 minus cos z to the power of n for 0 less than mod z less than 1, where m and n are positive integers. Then we have to discuss the nature of the point z is equal to 0 in terms of singularities. Before the discussion of the solution of the given problem, let us recall this theorem. This theorem is 8.19 theorem, and it is from a textbook by S. Ponnuswamy, and the title of the book is Foundations of Complex Variables. Right. If phi and g are analytic at a point z0, where phi has a 0 of order m at z0 and g has a 0 of order n at z0, then so we have phi and g are analytic at z0, and phi has a 0 of order m at z0 and g has a 0 of order n at z0, then phi by g has a removable singularity at z0 if m greater than or equal to n. So when m greater than or equal to n, phi by g has a removable singularity. B, phi by g has a pole of order n minus m at z0 if m less than n. So whenever m less than n, the z0 is a pole of order n minus m for the function phi by g. And you can see this result in the book Foundations of Complex Analysis. It's not complex variables. Foundations of Complex Analysis by Ponnuswamy. And this book seems to be very important in the point of view of the preparation of the CSIR National Eligibility Test. Agreed. Let's get into the problem. Let's now discuss the solution of the problem in detail. We have f of z is equal to sin z to the power of m by 1 minus cos z to the power of n, where 0 less than mod z less than 1 and m and n are positive integers, that is, they belong to the set of natural numbers. Let f of z is equal to phi of z by g of z, where phi of z is the numerator, that is sin z to the power of m, and g of z is the denominator of the function f of z, that is 1 minus cos z to the power of n. Agreed. And we have the expansions of sin z and cos z, that is the Taylor's expansions, which are valid on the whole of the complex plane. And they are sin z is equal to z minus z cube by 3 factorial plus z to the power of 5 by 5 factorial minus so on and so forth, and cos z is equal to 1 minus z square by 2 factorial plus z to the power of 4 by 4 factorial minus so on and so forth. Agreed. Now, phi of z we have taken it as sin z to the power of m, and that is equal to, in brackets, z in, and from this expansion we have taken out a z common, and we have written it as z into 1 minus z square by 3 factorial plus z to the power of 4 by 5 factorial minus so on and so forth whole to the power of m, and z is taken out, z power m into the remaining thing we have written as alpha z, where alpha z is 1 minus z square by 3 factorial plus z to the power of 4 by 5 factorial minus so on and so forth whole to the power of m, and we notice the value of alpha at z is equal to 0 is 1. Alpha of 0 is 1, which is not equal to 0. Agreed. G of z is equal to 1 minus cos z to the power of n. So we have cos z expansion, and 1 minus cos z will be, after the subtraction, you will get z square by 2 factorial minus z to the power of 4 by 4 factorial plus so on and so forth whole to the power of n. This is 1 minus cos z whole power n. And now z square is taken out, common, and when it comes out, it will come out as z square whole to the power of n, that is z to the power of 2n into the remaining part is beta z, where beta z is 1 by 2 factorial minus z square by 4 factorial plus so on and so forth whole to the power of n, and the value of beta when z is equal to 0 is 1 by 2 power n, which is not equal to 0. We continue in the next slide. That's what we have done so far. So this will imply phi of z is equal to z to the power of m into alpha z, and alpha of 0 not equal to 0 will imply z is equal to 0 is a 0 of order m for this function phi of z, and g of z is equal to z to the power of 2n into beta z, where beta 0 not equal to 0 will tell you that z is equal to 0 is a 0 of order 2n for this function g of z. So this will imply phi of z has a 0 of order m at z is equal to 0, and this g of z has a 0 of order 2n at z is equal to 0. Agreed. Let us recall that theorem 8.19 from the book of Ponuswamy, that is the foundations of complex analysis, and the theorem is here. We have already seen in the beginning itself, and now in our case, instead of, in the place of n in the theorem, we have 2n, and m is same. So applying this theorem to our case, then you will get, by theorem 8.19, we get f of z is equal to phi of z by g of z as a removable singularity at z naught if m greater than or equal to 2n. So in the place of n, we have 2n in our context, and phi of z is equal to, f of z is equal to phi of z by g of z as a pole of order 2n minus m. In the place of n, we have 2n minus m at z naught if m less than 2n. So now, we have applied this theorem and we got these results, and let us look at our options. And from these options, f of z has a removable singularity at z naught if m greater than or equal to 2n. That means option 1 is true, and the second one tells you option 2 is true, and option 3 is false because it is true only when m less than 2n, but it is given here in the option 3 m greater than or equal to n. So this will tell you option 1 and option 2 are true and option 3 is not false. is not true. Option 3 is not true. I'm sorry. Right. Sir, what about option 4? For option 4, I tell you this case, so this is not true. Why? Because all the choices for m and n we have already exhausted. That is, m greater than or equal to 2n and m less than 2n we have already exhausted. There are no other mn's left. Therefore, this fourth case does not arise and it is not true. Now finally, z is equal to 0 is not an essential singularity of fz for any values of m and n because we have already exhausted mn belongs to n, where m greater than or equal to 2n for removable singularity we have exhausted, and m less than 2n for the pole we have already exhausted. Therefore, we do not have any values of m and n. Therefore, z is equal to 0 is not an essential singularity. Therefore, option 4 is not true. So, the answer to this question is option 1 and option 2 are true. So, that is the detailed discussion of the solution of the problem on the singularities from the complex analysis. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.